Hello, Hubble huggers, and welcome to this week's Hubble Hangout. My name is Tony Darnell, and we've got a really great hangout planned for you today. Astronomers using the Hubble Space Telescope have been looking at this gigantic, very energetic, not invisible, but cloud of gas that is swirling around our Milky Way Galaxy, and they have used Hubble to characterize some of its properties. We're going to talk about how big it is, how fast it's going, what it's made of, and all kinds of things. So really excited to get going on that. But before I get started, I want to introduce my colleagues and cohorts in crime here. Dr. Carol Christian joining me again. She's the outreach scientist for the Hubble Space Telescope. Hi, Carol.
Hello. How are you?
And also, as always, Scott Lewis from knowthecosmos.com, who is doing a great job with driving our internet and monitoring the comments and everything else. So we are ready to get started with
and looking darn good while doing it.
Oh, of course,
Yeah.
Always looking good.
Yeah, modestly.
It starts already. Sorry.
It always starts.
I know this. Well, that's why. That's how.
I'm just letting you guys know what you're in for. This is what it's like.
So before I introduce our guest, I want to just mention real briefly that the last week in January is kind of a sad time for people who follow NASA and space travel and things like that. Of course, today marks the 30th anniversary of the Challenge disaster, so that's a very sad day. Usually we take a moment and think about that tragedy and what it has cost, and also, just the day before, in 1967, January 27th, we had the Apollo 1 fire. So we generally take a little bit of time this time of year and just kind of remember those folks who gave their lives in the effort of getting humanity into space. So it's always a little bit of a sad week here. But on a positive note, on a much more positive note, I was just before I joined the Hangout, I was following Alberto Conti's Twitter feed, and he announced that the last of the JWST mirror segments is being installed today. And so JWST is making progress and getting put together in a really what I think is going to be a big year for the James Webb Space Telescope.
Absolutely, huzzah, huzzah! Yeah, that's great.
All right, so let me. We're kind of switching things up a little bit this week in the way in which you guys are interacting with us. I think the Q&A has gone away now, the Q&A app, and so we got other ways. We would like you guys to leave us questions and comments and talk to us and our guests about the topic at hand today. And to do that is Scott Lewis. Go ahead, Scott.
Absolutely. So I know many of you have been used to using the Q&A app, and that's been awesome in many different ways. But what we're actually using this time is we're going straight through YouTube, so we're using the YouTube live event, and we have the live chat enabled. And I'm seeing people chatting already. So if you're heading over to YouTube right now, you can see us. We're chatting. I'll be in there as Hubble Space Telescope, responding to any questions in there. And if you have questions for the panel about the press release that just came out and the research that's going on, leave questions in there. Have conversations with the other viewers that are going on. Try to keep it civil, or I will delete it. But that's going to be a really great way for you to continue to engage with us and each other about the exciting news that's being released today. And then also, as always, we are still over on Twitter. We'll be live tweeting this event using the hashtag Hubble Hangout. So feel free to go over and follow us on Twitter if you're not already, at Hubble Telescope. And we'll be monitoring everything like that and ask questions, and we'll try to address them as we're going on throughout the show.
All right, good. Thanks, Scott. Well, as I mentioned a while ago, astronomers using Hubble have been following this what they're calling a high-velocity gas cloud, and it's being called, I guess, the Smith cloud. There's only one of them. It's not like a category of clouds, but this is a cloud named after, I guess, a doctoral student from the 1960s, Gail Smith. And so this cloud of gas is a very unique object that is sort of interacting with our galaxy, and astronomers using Hubble have learned a lot about it, actually. And the press release just came out today to sort of, in fact, it just went live this moment. And so to get to it, you can follow the link. I think it's in the description box below to follow along if you want to see some of the images and stuff that are being released in this Hangout or being talked about during this Hangout. But the astronomers that our guests today are the astronomers who have made the observations using Hubble, and with me is Dr. Andrew Fox. He's an ESA astronomer at the Space Telescope Science Institute. Dr. Nicholas Lehner, is it Lehner?
Yep, that's correct.
Okay. Oh yeah, I got it. He's a research associate professor at Notre Dame, and also is Dr. Jay Lockman. He's an astronomer at the National Radio Astronomy Observatory. So welcome, guys, and thanks for taking the time out to share your research with us. Let me start with you, Andrew, and maybe you could give us some background on this cloud. What is it?
Well, as you said, this cloud, the Smith cloud, was discovered back in the 1960s, so it's over 50 years old. But until recently, we really only knew about the hydrogen that exists in this cloud. We didn't know what else it was made of. We have a good understanding of where it is in the galaxy, how fast it's moving. It's coming towards the disk of the galaxy, and it's bringing in a lot of fuel that can end up forming new stars in the future.
Okay, so we found out about this thing back in the 1960s, as you said, but we only knew about the hydrogen in it. So, Jay, why was that? And that was because they used radio telescopes to find this thing at first. Is that correct?
Yeah, that's right. It was discovered using a radio telescope in the Netherlands by Gail Smith, as you say, a doctoral student, and she was mapping the hydrogen in the sky and found a signal from a cloud that was where it should not be. Most of the hydrogen in the Milky Way lies in the plane of the Milky Way, but this cloud was displaced from it by 10 or 15 degrees and was a very distinct object.
So
and
way out of the plane of the galaxy then?
Way out of the plane of the galaxy, and yet was very distinct in the radio emission from the 21-centimeter line of hydrogen. So she was able to measure its velocity.
Okay, good. So they knew hydrogen was there because hydrogen has this natural frequency that one can listen to it on. As you said, 1-centimeter line. So okay, so good. So for a long time, I guess we thought that was that. Is that all we knew about the cloud, Andrew? That it was mostly just hydrogen?
From the observational side, yes. We knew that there was hydrogen there. We knew that some of that hydrogen was neutral and some of it was ionized. But we didn't know about any heavier elements like sulfur and silicon and oxygen. But with Hubble, we've been able to study those elements because we can see the fingerprints they leave in the light of quasars, of bright sources of light that lie behind the Smith cloud.
Good. I want to get to that in just a bit because we've got some nice illustrations.
I do have a question. So there are other clouds, though, around our galaxy as well. Is that right?
Yeah, that's right, yeah.
Yeah. Okay,
Why
so
is this one cool?
If I could show me the cool. Explain to me why I care.
Well,
I'm just wondering why we picked this one. You picked this one.
Well, in fact, you're quite right, and a lot of astronomy is finding the one object out of many that tells a larger story than just about its history. And when you see the radio images of this cloud, you'll understand why it's cool.
Okay. Yes. So.
Okay.
Okay, so we've known about it for a long time. You wanted to learn more, and so you pointed the Hubble at it. Scott has an image up now, and Nicholas, let me get you involved here. Can you describe for us a little bit what he's showing?
Sorry, I can't see. Oh yes, all right.
Yeah, just click on his thumbnail. There you go.
All right.
Yes. Terrifying image.
Yeah, that's a terrifying image.
Yeah, that looks pretty ominous. It looks pretty ominous.
Yeah. So you see the Milky Way disk. That's a very dark absorbed region, but you see also this. That's toward the constellation Aquila, and then by showing basically how we will look like if you could see it in the sky. And so it looks.
So just to be clear, you cannot see it like this.
No, we can't just observe it. Even if we can't. Okay. So not with your eyes. So you can see it in the that's the H1. And what is very cool with this cloud, as Jay was saying, is that it has this cometary structure. It looks like it's going one way, and you can see head, and you can see a tail to this cloud. And typically the clouds that we see in the halo of Milky Way, they just don't look like this. So this one is really one in a kind.
Okay, so what? So from the hydrogen only, from the radio observations only, did we have a good idea? And maybe Jay, you can answer this. Do we have an idea how big it was with just those observations, or did we need these more in-depth observations from Hubble to get a sense of how big it was?
Well, to get a sense of how big it was, we needed to know its distance. And that really came from optical observations against stars. Do we see the cloud casting a shadow on a star, so to speak? And that was one of the three ways in which we determined its distance and its size.
Wait a minute. So you were looking at this thing in the optical wavelengths through telescopes, looking for shadows, or just the way it blocked out certain stars?
Exactly. If you would see the cloud in absorption against a distant star, then you knew it had to be in front.
Oh,
if you didn't see the cloud in absorption, then you knew it had to be behind the star. And astronomers working with ground-based telescopes figured out the best estimate of the distance to this, and from that we got its size.
Clever. Okay, well, so how far away is it?
It's about 30,000 light years or so, maybe 35,000 light years, about 12 kiloparsecs in that unit, and it becomes the size of a small galaxy.
Wow, that's amazing. And we also have an image, I believe, that sort of compares it with how big the apparent size would be with a full moon if it were up as well. But Andrew, let me ask. So let me get to the Hubble observation. So we knew roughly how far away it was, and also by extension, as Jay said, how big it was. What did you want to learn using Hubble? Why
I'm going to interrupt you again, but Jay just said something very interesting. It's
the
size of a small galaxy. So one might say, I wonder if it's a small galaxy that's crashing in. So I don't mean to preempt you, Andrew, but anyway, that he raised the question in my head.
Well,
maybe it's a small galaxy.
Maybe it is, and that's exactly one of the questions that we could address using Hubble, because we realized that if we found bright ultraviolet sources, UV sources that lie behind the Smith cloud, and we use Hubble to take spectra of those sources, so take the light and split it up into different colors, we could learn about the composition of the gas in the Smith cloud. When I say composition, I mean what type of elements, what type of atoms actually exist in the gas. Because the pattern that you see tells you something about where the gas came from. Did it come from the Milky Way versus did it come from being a different galaxy? And that was really the main idea of our experiment, was to use these Hubble observations of the background quasars to look at the chemical composition of the cloud.
Okay, and so you found that what did you find? What is it made of? Did you get
The main result we found was that this cloud is enriched up to about half the chemical composition of the sun. So we talk about solar enrichment as being how enriched in heavy elements like oxygen and sulfur the galaxy is near the sun. This cloud is about half as enriched in that. It's got about half as many heavy elements per hydrogen atom. And so what that tells you is it's actually similar to gas in the outer parts of the Milky Way. It matches the composition. It's really very similar to the outer parts of the Milky Way Galaxy. So the main result from this is that this gas looks like it came from the Milky Way. It's got too many sulfur atoms and too many silicon atoms in it to have come from being a small galaxy that collided with the Milky Way, because such an incoming galaxy would have had much lower levels of those elements.
Right. So the other options that were outlined in the press release was that it could, if it did not come from the Milky Way, it could have been a remnant of a failed galaxy. It could be the remnant of a failed galaxy that didn't have any stars in it, and this is a failed galaxy being just a bunch of gas, I guess, that never started any star formation.
That's right. Now, because if this really was a failed galaxy that had never formed any stars, then it would never have had any metal atoms like sulfur in it, because sulfur atoms are produced in stars. They get released in supernovae explosions. They have to come from stars. So the fact that we see these high levels of the sulfur tells you that this gas has been processed through star formation at some point.
So somehow this galaxy, or this galaxy-sized gas cloud, started in the Milky Way somewhere. I'm going to ask you where in just a minute, and then swirled around and is now about to, I guess it's heading back towards us, correct?
At the moment, it is heading towards the disk of the galaxy, and we have a reasonable orbit from the work of Jay Lockman, who's looked at the radio data of this and found that it came out of the disk of the Milky Way about 70 million years ago or so. What we don't know is what happened to it before that. Did it originate for the first time in the Milky Way, or did it come in from the other side of the galaxy, and what we're seeing is the leftover remains of it. So the original event that created this is still something of a mystery.
Okay, well, I want to go back to this, and we also have a comment here that I want to get to as soon as I talk about this image that Scott has up right now. He's got the cloud up with the comparison of what it would be like against a full moon, and I believe this. So you have this thing measured at about 11,000 light years long and 2,500 light years across. And so, so that makes it about 30 times larger than the size of a full moon. The galaxy, when you say it's like a galaxy size, for those of viewers who may not know, we have a companion galaxy, the Large and the Small Magellanic Cloud. How do they compare with those? How does the size of this cloud compare with the small galaxies that you were comparing it to?
Why don't you take this, Andrew?
Well, the question, it's not just the size of it, but it's also the shape of it. So if you look at the Magellanic Clouds, like the Large and the Small Magellanic Clouds, you see a much more round type structure, whereas this thing is really very elongated. But in terms, so this would be of similar proportions to a small galaxy in nearby to the Milky Way, but it's really a different shape. I mean, it's this extension of it, like a comet, as Nicola said earlier on. To me, that's what makes it stand out right now as appearing very different.
Well, the mass of a Smith cloud is also very different from the masses of Magellanic clouds. The Smith cloud is about 2 million solar masses, while the Magellanic clouds are about, if I'm correct, about 100 times the mass of that. So they are very different beasts than the Smith cloud.
So
and they're also forming stars, which the Smith clouds, as we know,
Magellanic clouds are.
the Magellanic clouds are, and the Smith cloud doesn't.
Yeah, we don't know of a single star in the Smith cloud.
Okay, so and you were mentioning the masses. What did you say the mass was again? I'm sorry.
It's about 2 million solar masses. And,
how do you get that? I mean, how do you determine the mass of something?
Well, I'm going to let Jay to answer that question because he has derived it.
Yeah, that comes very simply from measuring the amount of hydrogen that we see and the distance. It's a very precise measurement. And I should say that the image that we're seeing there with the full moon, and what really broke open study of this cloud, for me at least, was that we finally, with the Green Bank telescope, which is in the lower right-hand corner, had the acuity, the ability to see that this wasn't just a blob on the sky, but was all this fantastic detail and this cometary shape. We can see it being torn apart by its interaction with the Milky Way.
Okay, so you know that you have a rough idea not a rough idea. You've got an idea that this came from our own Milky Way. That it's not a gas cloud coming from from outside the galaxy, nor is it a failed galaxy. And you've gotten a good idea of its mass and its size. And what about its speed? How did you figure out its trajectory and where it's going? And we had you've done some amazing observations on that as well, right?
Well, we get a measure of its speed from its Doppler shift, and that tells us its speed away from us or toward us. And it has a very peculiar velocity for where it is in the sky and in the Milky Way. That's how it became to be cataloged as part of these clouds, which don't necessarily share the rotation of the Milky Way. They have a peculiar velocity. But the Smith cloud is so large that we can actually get a measure of its velocity to the left and right. And if you think about a Doppler shift and a train, then while you're standing at a railroad crossing, the part of the train that's right in front of you has no Doppler shift. It's going across your line of sight. But the front of the train is going away from you, and the back of the train is coming toward you. And by measuring that subtle shift in velocity across the cloud, we can estimate its direction of motion.
Oh, nice. Okay. Well, I believe I saw a graphic that showed various trajectories with background objects. Scott, could you put that one up? And we'll talk about that as soon as you get it up. But so you measured using oh, there it is. Yes. So this is one of the ways in which you got a trajectory for it, correct? What Scott's got up now?
No, that's how we got the amount of sulfur. That's
Okay.
the Hubble observation.
Okay, well, let's talk about this then. So you looked at the light that came through the cloud from these AGNs, these active galactic nuclei, and the spectrum up above shows what they're made of. Andrew, can you speak to this just a little bit?
Yeah, sure. So what you see in those panels at the top of the figure is a simplified version of the radio data in the top halves of each panel and the Hubble ultraviolet data in the lower half. Because what the radio data gives you is an emission signal. It gives you a little bit of extra light coming from the Smith cloud compared to the background nearby. When you look in the Hubble data, you're seeing what we call absorption, where you see a little bit less light because some of it has been taken out by the cloud. But what we find is always a match-up, a correspondence between where do we see the emission in hydrogen and where do we see the absorption in sulfur. And that's how we really identify that we know we're seeing the Smith cloud or we're not seeing something else in the data. It's by matching them up in velocity. And then comparing the strengths of those lines gives us a measurement of how enriched in sulfur the gas is.
And because of the different lines of sight, you can get different compositions at different parts of the cloud too, correct?
You can do. Now, we found for 2 of the 3 sight lines, we got a very similar answer for what the abundance of the gas is. And we found for the sight line that was in the wake of the cloud, kind of towards the back of it, we got a slightly lower abundance. But ideally, we would need even more sight lines to see if there was a gradient that as you go further and further and further down the cloud, is that abundance changing more and more? We're not quite at that point yet because we don't have the targets to do that.
And the reason that you have velocity on here, this is Jay's analogy to the train, right? So one side, So
these are Doppler shifts.
So they're Doppler shifts. So this is like looking at the train going past us.
Mm-hmm.
Good. Yeah, I think that's good. That's a good clarification. So now, so this is how you got the composition of the sulfur. And I want to go back, Scott. There's another illustration showing the trajectory of this. If you could put that up, and then and then I'm going to get to you guys' comments. There's 2 good comments that Scott has queued up here from Lee Critton and Julius Green, and I'll get to those in just a minute. But before I do, I want to talk about how this thing is moving across the sky a little bit, and then we'll go into what might have caused its shape and kicked it off and doing all this kind of stuff. So here is a trajectory. It's very pixelated for me, but I've got this. Oh, there we go. Okay.
Yeah, I made it pretty for you guys.
You did. Very nice.
Oops.
Oh, there's a traffic cone too. I didn't know there was. Okay.
Well,
so who wants to
I
tell me
had to put a
about?
pause on. There was a collision going on.
Oh, okay. Well, I'm glad you're being safe.
All right.
So
LA
who wants
traffic.
to tell us about what this is? Nicholas?
Yeah, sure.
Okay.
So, the first frame that we're seeing is about 70 million years ago. That is where the Smith cloud may have come. It's the outer edge of the Milky Way galaxy. And the composition in the outer edge of the Milky Way is actually very similar to what we're finding in the Smith cloud. That's another reason why we're saying that it may actually come from the Milky Way, not just passing through the Milky Way. The second frame is it's basically today. That's when we observe the Smith cloud, and in the last frame we know that it's going back onto the Milky Way disk, and is going to collide and crash onto the Milky Way disk. And our understanding of what's going to happen is that when it's going to do that, we may have a lot of new stars that's going to form within the Milky Way. And actually, we think that there may be about 2 million suns that may actually come up from this collision between the Smith cloud and the Milky Way disk. And that's important because, if you look, we know for a very long time now that galaxies are not closed boxes. They need a fuel to continue to form stars over billions of years. And the Smith cloud really gives us this impression, this visualization that, there is gas that is, and we know there is a lot of gas around the Milky Way, but the Smith cloud is the only one that really we know where it may have come from, and that is actually going back. And so we know that means that the Milky Way is actually recycling some of its gas to form stars. That's basically the end result here.
Okay.
So I have two comments about this. The first is I think you're not going to get observing time to watch the crash, and and I'm anticipating that Tony is going to ask you, why did this cloud come out of the Milky Way?
I do want to talk about that, but before I do, I want to just go back to what you said about the star formation. When it does collide, we've already said this is about the size of a small galaxy, and so this can kind of be thought of, can't it, as sort of a little miniature galaxy collision, because you're saying stars are going to be born when it collides.
Yeah.
So what is it colliding into? We all know that when galaxies collide, that the stars don't actually hit each other; they sort of pass through. So what specifically is going to trigger the stars forming when it does hit the disk? And then I promise I'm going to get to your questions, guys.
Okay. Andy, you might want to take this.
Sure. Well, so this gas cloud is going to ram into the disk of the Milky Way about 30 million years from now, as we saw in that orbit figure. And when that happens, the gas can be compressed because there's already existing gas in the Milky Way disk. We call it the interstellar gas of the galaxy.
That's where I was going with it. Okay,
so
good.
You take this incoming Smith cloud and you slam it into the interstellar gas, then you have two regions of gas that can be compressed. And when they get compressed, they can become more dense and ultimately form stars. So it's a little different from if you take two galaxies and you just combine stars, because as you say, Tony, those stars can just go right past each other. Here we've got gas colliding with gas, and that's a much more likely situation where you can get stars.
And that's really what's going on with the galaxy collision anyway, isn't it? Yep. I mean, when galaxies collide, it's really their gas that's causing this burst of star formation anyway. So
exactly.
It's like having a galaxy collision without the stars is really about the same. Cool. Mm-hmm. Okay, well, so we know this thing is moving. It's coming back at us at about 700,000 miles per hour is what the press release is saying. And we're going to get some great stars out of this when it does come back to us. And Julius Green is asking, maybe it has been flung out by a passing of the Magellanic Clouds, which we've talked about a little bit. And Galaxy is also asking, what could the original events be? When I look at these gas clouds swirling around, it reminds me of an analogy of the Earth's crust. You know how active the crust is? It always is moving, and it's, Mars, by example, doesn't have a lot of plate tectonics, but the Earth renews its surface every so often, so it's very active. This is kind of an indicator of how active a galaxy can be too, right? And what do you suppose might have kicked it off?
Well, I would say there are a couple of main theories that are out there, and one of the two main ones is supernovae, or a cluster of supernovae in our own galaxy. If you had some stellar explosions that went off in the outer disk of the galaxy, they could have blown some material out into the halo, some of which could have then formed into a cloud like the Smith cloud. This kind of makes sense because we know that supernovae expel gas and produce material up in the halos of galaxies. But the problem is that this cloud seems a little bit too massive to be made by those types of events. It's much more massive, the 2 million solar masses we talked about of gas in a Smith cloud, that's much more than you see around other supernovae type shells that are found in the disk of our galaxy. So that brings me to the other possibility that I think is a very interesting one, which is whether or not something came in from the other side of the galaxy, passed through the disk, and picked up the material as it came through. And what that something could be a region of dark matter. In the research, people talk about a halo or a mini halo of dark matter. If that were
Yay, dark matter!
Yeah, that could be what's at work here. If that had come in, bombarded the disk, and then picked up some gas as it passed through, what you might end up with is this way of moving gas around from one part of the disk to the other, as if it was catching a ride on this dark matter halo. And that,
so a clump of dark matter not necessarily associated with our galaxy, but might be in the halo, as you point out,
Yes.
may have passed through and perturbed this. Would it need to have been roughly the same size as the gas cloud itself, the dark matter clump, or would it have been? Do you have any idea how big the thing might have had to be to make it go? You said a supernova would be too small, probably.
In terms of the energy, yes. Jay, I don't know if you might want to chime in on this,
Sure.
but there has been a lot of work on the dark matter model of creating this.
Okay.
Yeah, the mass of dark matter would be perhaps 100 times the mass of the gas that we see now. It would be dominated by dark matter. Because as you see Smith Cloud right now, one of the things that makes it so striking is its cometary appearance. But this is indicating that even now it's being torn apart as it encounters the most tenuous outer parts of the Milky Way's gaseous layer, and also being stretched by tidal forces. And so there is some thought that it must have dark matter even to get as close to the Milky Way as it is right now. And as Andrew said, a clump of dark matter passing through the outer disk might have been able to pick up this much gas and then just bring it along the trajectory we currently see.
Okay, well that gets to Lee Critton's comment or question where he was asking, when you were talking about the shape, he was saying, is it the shape? It is because of the strength of the gravity over a distance that big, and what you're saying is that it's being stretched and pulled by even the tenuous gas that it's running across right now, correct?
And also by gravitational tides, though. Tides stretch it as well, yeah.
All right, so this... So how can you find out if that was what it was? I mean, how do you know? It's easy to say dark matter did it because it won't interact with us in any way, shape, or form. And so how can we narrow that down a little bit? Is there a way we can do that? I know we can rule out some things, but can you actually say it's dark matter for sure?
Well, we do need better simulations, because one of the issues here is if you take a dark matter halo and you run it through the disk of the Milky Way, you need to ask how much gas can it pick up? How much can it accumulate before it comes out of the other side? And this is something that the theorists that work on computer simulations of clouds like the Smith clouds are looking at, is can you accrete a lot of gas onto a dark matter halo as you come through? And so I do think that the simulations are going to play a large part in answering that question of, is this dark matter that's going to explain all this?
Okay, well, Galaxia has a good question about the trajectory when it's coming back down, and he or she, I'm sorry, I don't know which one. He is asking, will it touch our neighborhood too? So will the gas come anywhere near the sun when it does come through?
No, we don't believe it will come anywhere near the sun. But what's intriguing about this kind of line of thought is that it was proposed some years ago that an event like this did happen near the sun. The brightest stars around the sun are not in the same plane as the Milky Way. They lie in what's called Gould's Belt, with Orion below the Milky Way and Ophiuchus above the Milky Way. And the brightest stars are also around the sun are actually in a ring that's expanding slightly. So people have hypothesized that in the past, a cloud of gas, perhaps like the Smith cloud, hit near the sun at an oblique angle, creating these new stars somewhat displaced from the Milky Way.
So that would be a characteristic we'd expect to see of a cloud, stars formed from a cloud like this, is they wouldn't fall in traditional, I guess if you can call that, if that's the right word, traditional places you'd expect stars to be.
Certainly, yeah, that might be the case, yes.
Nice. Okay. Well,
Does this have anything to do with galactic fountains, or are those completely different phenomenon?
well, that sounds so pretty. I want a galactic fountain.
Well, this was. I'll take that unless you want to do it.
We have some in our backyard, but
The model that Andy talked about of supernova launching gas is the galactic fountain model.
Yeah.
Yes.
yeah, that's what I thought.
Okay, galactic fountains, nice. So, Kieran,
I've been trying to get one installed in my foyer, and it's just
I'm going on
such a
Amazon
pain.
right after this.
Getting a contractor in Southern
I'm
California
not
to put
sure
it
you
in.
want to do that. I would not recommend that.
I can't get the permits for the life of me.
I don't think. No, not a good idea.
I can. Well, thanks for the warning. Maybe I'll wait. All right. So, what about a black hole? Kieran Mulvey is asking, could there be a black hole at the very tip of the cloud? Any chance that dark matter could disturb things like black holes? Or
yeah, I'm seeing a lot of discussion in the chat here about black holes. Do we have any idea about anything regarding black holes in this mass?
Yeah.
You know, I mean, obviously you can't see a black hole, but we can see its effects on the material around it and its interaction. And black holes tend to be kind of bright radio sources. They tend to be X-ray sources. As the matter around them is swept into the black hole, they give off lots of energy. We really don't see anything like that in the vicinity of the Smith cloud that we can actually identify with being part of the Smith cloud.
Okay. Well,
but back to answer a previous question as well, as can we really distinguish the dark matter model? Andy gave part of the answer, I think, in that we need to do better simulations, but also if there's more matter out there than just the gas, then we should somehow be able to see the gas reacting to that extra gravity. And if we get a good model for the cloud where it is now and look at the internal velocities that it has that supports the gas against that gravity, we might be able to actually get an estimate if there is any matter missing that we can't be accounted for by the gas itself.
Oh, okay, good. So, and I don't suppose that the trajectory or the dark matter, I don't suppose there's anything that suggests that maybe the dark matter is going along for the ride or anything like that. I guess, is there? I mean, is there any way you can...
It's kind of the opposite. The dark matter just plows along, and it's the gas that's along for the ride.
It just does whatever it's going to do. So Carol alluded at the top of this that this is a cloud. It happens to have a name. There are many more, some of them fountain-like. Are we looking at any other gas clouds like this, or is this one just the most interesting, the brightest, and whatever in these wavelengths? Are there any other areas that we're looking in the Milky Way for these things?
Yeah, we're studying a whole population of these high-velocity clouds that exist in all directions around the Milky Way. This one of the most interesting things is how close to the disk it is. We talked about how in about 30 million years it's due to run into the disk and form new stars. 30 million years isn't that long in the lifetime of a galaxy, right? Because we are thought to be maybe 10 billion years old or so as a galaxy. So this is not long at all for the gas to come in. So we're really looking at something close to the disk. A lot of the other high-velocity clouds that are studied right now may be further away than this one.
Okay, that always blows me away that the age of our galaxy is measured. It's that old. I mean, I always thought, you look at some of these like ellipticals, really old galaxies, and this is 10 billion years is pretty old. That's amazing. And stars are still being born, stars are still forming, and we're still colliding with other galaxies. We will be colliding with other galaxies in about 2.5 million years. So it just it's astonishing to think about that as the age of our galaxy.
So I have another question, of course.
Yes, Carol, where's your
Carol? You're running out. We're in January 2016. We need a. It's not a sprint.
What's your question, Carol? Come on.
My question is.
Oh, we're out of time.
My question is, have you seen or do you know of any similar things that happen in other galaxies that are analogous?
Oh, that is a good. I'm glad we let you ask that. That's a good question, Carol. Yeah, what about the Andromeda Galaxy or other galaxies like ours? Do we see this kind of stuff going on?
Well, we do see certainly lots of clouds around Andromeda, and but there are no clouds that look like the Smith cloud around Andromeda. That has this cometary.
Aren't you being
Well,
a little centric?
we also don't have that kind of detail
So-
yet on the clouds around Andromeda.
Yeah.
Okay.
Yeah.
All right.
We do see other clouds there, though. Nicholas is absolutely right.
So, do you see them in radio like the ones you started here, or what are you seeing them in? For example, around Andromeda.
Well, we see in a radio emission, yes, like the Smith cloud, but we also started to study them in the ultraviolet, and that was what we discussed last summer about the discovery of this giant halo around Andromeda. And so some of this cloud is detected also in the UV.
Okay. So, Dennis Arboleta is asking a question that's similar to one we asked about the Magellanic Cloud maybe being the cause of these things, but or at least what kicked it out. And he's asking, can it be the rest of a very old galaxy collision between our galaxy and a very small one, or a collision between our galaxy and a small gas cloud? So we've already said that it might be dark matter, it might be some explosions here within our galaxy. What about old galaxy collisions? Some remnant of some other past interaction?
I think that's a really great possibility, and it could work in a kind of hybrid sense, in that if there was an older galaxy that collided with the Milky Way and then picked up some gas, you can end up producing something that looks like the Smith cloud. But you still have to pick up that Milky Way gas to give it the abundances, the sulfur enrichment levels that we seek. So you can start with an old neighbor of the Milky Way and collide it with our galaxy, but you do still have to modify it to produce something that looks like the Smith cloud. And that's why for a long time people weren't so sure whether these models of satellite galaxies could really explain the Smith cloud, because it didn't have stars. It doesn't look like a galaxy. And it's only if you modify it through the collision that possibility could work.
Okay. I guess it's Total Eclipse. Is that the username, Scott, that you put up here? Anyway.
Yeah, it's Total Eclipse, not of the heart, but just a Total Eclipse. Total Eclipse of the question mark, because there's a lot of question marks. No, I put the question mark in there because it was an interesting question that I...
Yeah, so it's a comment. He's saying it's being attracted by the Hydra Centaurus supercluster called the Great Attractor away from the zone of avoidance. I did not understand anything I just said. So
Neither did I, which is why I put 6 question marks ahead of it.
Okay. Does that make sense to anybody?
Yes.
Well, I think that the gravity that the Smith cloud is currently feeling is overwhelmingly dominated by the gravity of the Milky Way, and not by the Great Attractor.
Okay. Well, since we brought it up, what is that? Is it
besides me out in the town, what's the Great Attractor?
Oh my God.
Why?
Yeah, the Great Attractor is hypothesized to be a group of galaxies that are hidden by the dust in the Milky Way from being detected in their light. But we detect them by looking at the motion of other galaxies.
Got it. Okay, well, see.
But that's on a much, much more larger scale than the Smith cloud and the Milky Way.
Right.
Okay,
And one thing to remember with gravity is we're dealing with the square of the distance, and so we're having, the closer you are to something, the more of a pull it's going to have. So something so far away, even if it is way more massive than our Milky Way, it's closer to the Milky Way, so it's going to have that pull.
Right.
Yeah. So I guess the Hydra Centaurus supercluster must be in reference to some large-scale structure neighborhood.
Sounds like a great Asimov novel.
Yes.
I mean, you name my sailboat that. That's really a cool name. Okay. All right. Well, good, Scott. I think we've gotten through those comments. How about Twitter and the other verses that you're keeping track of?
Everything on Twitter we've actually already responded to, which has been great. This conversation has been awesome. So we've really been on top of responding to the questions as they're coming through. Let me see here. I'm going back to the chat because it's been rapid fire. So thank you, everybody. I'm glad that we switched to the live chat.
Is the chat window a good thing?
The chat window is awesome. I'm loving the chat window, and everybody else seems to
is
be
like,
like,
no, let Carol ask her question, please. We did.
oh, and yes, by all means, Carol is really in charge of us. We're scared of her.
I actually am. I'm in charge.
So,
not at all.
I give Carol a hard time because I'm afraid of her. And
this is talking about action at a distance. Scott is a very far away.
Yes, I'm very far away because she has a long reach.
If you've got a moment, I've got a question for Andy and Nicola.
Yeah.
Okay.
And that is, would you have guessed that the answer, before we did the experiment, would you have guessed that we got this answer?
I know I wouldn't, because I thought we would either get about solar metallicity or maybe 1/10 solar, and it came in at 1/2, so right in the middle of the two possibilities that I expected.
Well, by
So
metallicity, you mean
what you're gonna
percentage of heavier elements, correct?
Yes.
Yeah.
Thank you for clarifying that. So I had kind of two ideas in mind, a high value and a low value, and it came out right in the middle of those two when we measured the enrichment.
Yeah. I'm the same. I would have probably say low metallicity, much lower than what we had. So it's a surprise actually.
All right. Well, so you've done a pretty good job characterizing this cloud. You know the size. You know more. You know what it's made of. You know where it's going. Is there any future work that you're going to be doing on this in this research field? And I'll leave it to either of you or all of you.
I think one aspect that can be addressed a little bit more is the fragmentation and the fate of it. You know, we think a lot of this gas is going to get into the disk and form new stars, as we've said, but we can see that the cloud is breaking apart because of all these forces, the tidal forces and the gas pressure. So we want to see how extended is it in the wake and in the larger region around the Smith cloud, because it might not come into the galaxy in one piece. It might come in fragments, because we can see some of that fragmentation already happening.
Yeah, that's what Jay was alluding to earlier.
So it would be good to get just a handle of exactly how extended that process is across the whole cloud.
Okay, good. So how about you, Jay? Do you have any future observations planned or work?
Yes. You know, the scale of this on the sky is kind of hard to imagine. It's bigger than the Orion constellation, and we have by no means mapped out its full extent on the sky. So there are pieces scattered all about, and I hope in the next year or so to be hunting a few of these down. And also, it is, as it's being torn apart by its interaction with the outermost parts of the Milky Way's gas, we have a chance to learn something about the gas that it's encountering, which we don't know a lot about. And so I'd very much like to extend this Hubble work to some different directions where perhaps we have an opportunity to study the actual interaction of this cloud with the Milky Way right where it's happening now.
Wow, you would have to, because otherwise you have to wait, what was it, 30 million years?
30 million, yeah.
Carol already said you're not getting time for that. So.
And then it's going to be very far away from us, unfortunately. It's in a great place to study right now, but as it gets closer to the Milky Way disk, we're going to lose sight of it.
Okay, well, good. And Nicholas, any comments on the future of future work?
Well, what I'd really like is, I love the Hubble, but what I'd really like is a super Hubble, to have many more.
Super Hubble?
Yeah.
Do you mean JWST?
Well, not JWST, because we truly need the UV light, and so the JWST is not going to be able to do that. But what we'd really love to do is to have, instead of having only 3 background targets, is to have like 10 or 20 targets behind it. And with that, we will nearly, there is, for example, a gradient in the chemical composition of this cloud, which will tell us more about its origin and where it comes from. So, yeah. So
in order to get those additional targets, more accurate, right?
But we may have to wait at least 20 years, which is maybe the timeline for the next super Hubble missions.
Okay,
Yeah.
would that be? I guess that'd be PST, wouldn't it? Okay.
Yeah.
All right. Well,
exactly.
All right. Well, we have a comment or question from G+ from Camille Carlisle. What observations will you need to determine the internal velocities of the Smith cloud and determine if it has a dark matter component?
Let me take that.
Okay.
We may have most of the observations that we need already. It's just a matter of getting around and analyzing them theoretically.
Okay, good question. Okay, well, Scott, anything left on the in Twitterverse that I've missed?
Let's see here. Twitterverse, no. YouTube, let's see here. We did touch on this earlier, but it's, I'm sorry if I mispronounced this, but Yuan Biao. But what's causing the cloud's rotation? Did we already talk about this? So we are talking about velocities, and velocity is the speed and direction, and also we're talking about gravity. So I believe we're talking about its rotation being because we're able to see its velocities. Is that correct, everyone?
Well, I think you said that it was kind of being stretched and pulled by the tenuous gas of the Milky Way. That's correct. That's one motion, but I don't know if you talked about any kind of rotation.
Yeah, we haven't really covered that in the Hangout today. It's more the motion directly towards the galaxy along this trajectory that we can map out that is better understood than any internal rotation of the cloud.
All right.
We really don't see any rotation.
Okay, good. So
there could be a little bit hidden.
And that goes to Evelyn Graff's comment or question, I think, where she says that there appears to be tornadic vortices in the. That would just be. That's not exactly. That may not be indicating any kind of rotation more than it would be just the sort of pulling of the cloud itself. Correct? Those are just structural features in the cloud.
Right. Turbulence, the interaction of the cloud with the gas around it.
Oh, here's a good question from Craig Landon. I'd like to know the answer to this. We're talking about radio. What about ALMA? Can you use ALMA to do any investigating on this cloud?
Well, unfortunately, we don't know if there are any molecular parts of this cloud. The gas that we've seen in it is mostly neutral and ionized atoms, but ALMA looks for molecules.
Oh, okay.
This gas is really too diffuse. It's too low density to have the molecular part of it. So I think it would be very tough to detect this object with ALMA.
Okay, that's a great question, though, Craig. Thanks for that.
Yeah.
So just to clear up, the molecules are two atoms or two or more atoms stuck together, while ions are basically an atom that is either missing an electron or has too many, whatever in there have a charge, and so those are individual atoms. And that's what you're looking at here with the 21 centimeter line of hydrogen, as well as other things, the spectra that you were looking at to get the get the other components. So okay, so ALMA not so much. I guess that would be. Are there any molecular clouds doing this kind of thing, or mostly is it just these atomic ones?
They are mostly atomic and ionized cloud. We have found a few molecular cloud, but they are very, very rare.
Okay, and would they be located more in the center of the galaxy, or does it just
no,
where?
Not as far as we know, but we have only found one or two, I think, at high, far above the galactic plane. So.
Well, that is rare. All right.
Yeah.
Well, I guess that covers this week's Hangout. This has been a really great discussion. I want to thank all of you. I want to thank Dr. Andrew Fox, Dr. Nicholas Lehner, and Jay Lockman from the National Radio Astronomy Observatory. Thank you guys for taking time out to talk to us about this. The press release, guys, if you guys want to read it, I think Scott put the link in the description box.
Yep, so everything's in the description. It's on YouTube, Facebook, Twitter. But the best way is if you head on over to hubblesite.org, and our newsletter's the top thing up there.
Yep. Hubblesite.org, and go to the press releases or the news center, and you can read more about it. So, but you heard it here first.
Yes, right.
Oh, I want to point out, if you want to learn more about these Hangouts, I meant to do this at the top of it. Scott and I are sort of switching things up a little bit. If you want to learn about the next Hangout, let us know you're coming, which we would very much appreciate. Scott is now doing these events on our Facebook page. Scott, you want to just briefly summarize that?
So if you haven't liked our Facebook page, please go do so. We are the Hubble Space Telescope. So you can head on over there, and when you go to our events, you'll be able to see the event page. You can subscribe to that. So anytime that we're doing another event or hangout or something like that, you'll be notified of it and you can join it, and we keep the discussion going on in there. We embed any of the videos and the images that are going on, so you're able to keep up with the action here and hop on over into the YouTube chat like so many of you guys have been doing. It's been awesome. But you can stay in touch with us on Facebook, as well as still over on Twitter and Google Plus, and on Instagram. We're official Hubble over on Instagram as well.
That's right. And okay, so yeah, that's a good way to get notified and let us know you're coming. And you can also subscribe to that page and get all kinds of notifications about this event and any other hangouts that we might do as well. Carol, are you there?
I'm here. I've received 3 phone calls at the end of this hangout, so it's like now time.
You got to get you going. You're a busy woman.
So, 1 at the beginning and now 3 at the end. I don't know.
I know. So okay, we'll let you go to answer your phone calls.
No, I'm not. I'm ignoring my phone calls. I just think it's amusing that on these hangouts now for the last 3 weeks, we've had a phone call at the beginning and a phone call at the end.
You're just popular like that.
No, I think it's random.
Well, you answer my phone calls, so I feel loved.
Of course. Anyway, no, that's good. And I next week will be a surprise again.
Okay, good. So that's where I was heading with this. I was wondering if you had a plan for next week's Hubble Hangout.
I do in my head, but it's a surprise.
Even more important that you subscribe to that Facebook page to find out what it's going to be. Because it'll be, without question, very Hubbly and exciting. So, so thank you guys. Okay, guys. Well,
thank you.
Yeah, it's been a really great hangout. I want to thank our guests one more time.
Much.
And on behalf of Carol Christian and Scott Lewis, I want to thank you all for watching. And as always, keep looking up.
Yeah.
It'll be a big year for the James Webb Space Telescope.
Absolutely. Huzzah, huzzah. Yeah, that's great.
All right, so let me. We're kind of switching things up a little bit this week in the way in which you guys are interacting with us. I think the Q&A's gone away now, the Q&A app, and so we got other ways. We would like you guys to leave us questions and comments and talk to us and our guests about the topic at hand today. And to do that is Scott Lewis. Go ahead, Scott.
Absolutely. So I know many of you have been used to using the Q&A app, and that's been awesome in many different ways. But what we're actually using this time is we're going straight through YouTube right now. So we're using the YouTube live event. And we have the live chat enabled. And I'm seeing people chatting already. So if you're heading over to YouTube right now, you can see us. We're chatting. I'll be in there as Hubble Space Telescope, responding to any questions in there. And if you have questions for the panel about the press release that just came out and the research that's going on, leave questions in there. Have conversations with the other viewers that are going on. Try to keep it civil, or I will delete it. But that's going to be a really great way for you to continue to engage with us and each other about the exciting news that's being released today.
Using Hubble, and with me is Dr. Andrew Fox. He's an ESA astronomer at the Space Telescope Science Institute. Dr. Nicholas Lehner, is it Lehner?
Yep, that's correct.
Okay. Oh yeah, I got it. He's a research associate professor at Notre Dame, and also is Dr. Jay Lockman. He's an astronomer at the National Radio Astronomy Observatory. So welcome, guys, and thanks for taking the time out to share your research with us. Let me start with you, Andrew, and maybe you could give us some background on this cloud. What is it?
Well, as you said, this cloud, the Smith cloud, was discovered back in the 1960s, so it's over 50 years old. But until recently, we really only knew about the hydrogen that exists in this cloud. We didn't know what else it was made of. We have a good understanding of where it is in the galaxy, how fast it's moving. It's coming towards the disk of the galaxy, and it's bringing in a lot of fuel that can end up forming new stars in the future.
Okay, so we found out about this thing back in the 1960s, as you said, but we only knew about the hydrogen in it.
And then also, as always, we are still over on Twitter. We'll be live tweeting this event using the hashtag Hubble Hangout. So feel free to go over and follow us on Twitter if you're not already, at Hubble Telescope. And we'll be monitoring everything like that and ask questions, and we'll try to address them as we're going on throughout the show.
All right, good. Thanks, Scott. Well, as I mentioned a while ago, astronomers using Hubble have been following this what they're calling a high-velocity gas cloud, and it's being called, I guess, the Smith cloud. There's only one of them. It's not like a category of clouds, but this is a cloud named after, I guess, a doctoral student from the 1960s, Gale Smith. And so this cloud of gas is a very unique object that is sort of interacting with our galaxy, and astronomers using Hubble have learned a lot about it, actually. And the press release just came out today to sort of, in fact, it just went live this moment. And so to get to it, you can follow the link. I think it's in the description box below to follow along if you want to see some of the images and stuff that are being released in this Hangout or being talked about during this Hangout. But the astronomers that are our guests today are the astronomers who have made the observation.
I'm just letting you guys know what you're in for. This is what it's like.
So before I introduce our guests, I want to just mention real briefly that the last week in January is kind of a sad time for people who follow NASA and space travel and things like that. Of course, today marks the 30th anniversary of the Challenge disaster, so that's a very sad day. Usually we take a moment and think about that tragedy and what it has cost, and also just the day before, in 1967, January 27th, we had the Apollo 1 fire. So we generally take a little bit of time this time of year and just kind of remember those folks who gave their lives in the effort of getting humanity into space. So it's always a little bit of a sad week here. But on a positive note, on a much more positive note, I was just before I joined the Hangout, I was following Alberto Conti's Twitter feed, and he announced that the last of the JWST mirror segments is being installed today. And so JWST is making progress and getting put together in a really what I think is going to. Hello, Hubble huggers, and welcome to this week's Hubble Hangout. My name is Tony Darnell, and we've got a really great hangout planned for you today. Astronomers using the Hubble Space Telescope have been looking at this gigantic, very energetic, not invisible, but cloud of gas that is swirling around our Milky Way Galaxy, and they have used Hubble to characterize some of its properties. We're going to talk about how big it is, how fast it's going, what it's made of, and all kinds of things. So really excited to get going on that. But before I get started, I want to introduce my colleagues and cohorts in crime here. Dr. Carol Christian joining me again. She's the outreach scientist for the Hubble Space Telescope. Hi, Carol.
Hello. How are you?
And also, as always, Scott Lewis from knowthecosmos.com, who is doing a great job with driving our internet and monitoring the comments and everything else. So we are ready to get started with
and looking darn good while doing it.
Oh, of course, always looking good.
He added modestly.
It starts already. Sorry.
It always starts.
I know this. Well, that's why. That's how he's.